It can shatter in an instant, yet its legacy is measured in millennia. Every year, human activity generates over 2 billion tons of waste, and glass accounts for nearly 20% of this staggering total. A single bottle, if discarded in a landfill, can persist for more than 1 million years without decomposing. But this material holds a remarkable potential. Glass can be recycled an infinite number of times, reborn again and again, without any loss of quality or purity. The process transforms a chaotic jumble of broken fragments into clean, shimmering new forms. To understand how, we venture into one of the world's largest glass recycling plants. Within these walls, hundreds of tons of glass are given new life each day, revealing the incredible journey of one of our planet's most sustainable materials. It begins not in a factory, but on a city street corner. A single empty bottle, its journey far from over, is placed into an automated return machine. Across many European cities, this system elegantly solves the costly problem of sorting glass from household trash. The machine scans each container, sorts it internally, and issues a small refund, usually between 10 and 20 cents per bottle. A freshly finished drink is instantly transformed from potential waste into a valuable asset, creating a powerful incentive for public collection. This approach delivers a steady stream of pre-sorted, clean, and remarkably consistent glass directly to the recycling industry. Once these reverse vending machines reach capacity, specialized trucks are dispatched to collect the contents. Using forklifts, crews load large plastic bins, each one brimming with thousands of empty glass bottles, onto the truck beds. A single full-size vehicle can carry a payload of 20,000 to 30,000 bottles, a weight of about 10 to 12 tons of raw material. Loaded with their fragile cargo, the trucks make their way from supermarkets and urban collection points to the recycling plant. Upon arrival, the drivers back up to a vast storage bay and release their load, sending a cascade of glass tumbling down onto the concrete floor. In moments, colorful mountains of green, brown, and clear glass begin to form, sparkling under the facility lights. These piles are not an endpoint, but the very genesis of the entire recycling chain. A raw material supply waiting to be cleaned and crushed. A mountain of discarded color and light awaits its violent rebirth. From towering piles, massive loaders carve out their share of the waste glass, hauling their heavy burdens across the yard. The journey begins with a deafening roar as the glass cascades into the plant's feed hopper, sending a river of shards onto a steel conveyor. This stream of glass, dirt, and sand travels deep into the facility, where its first trial is a vibrating screen. Powerful oscillations shake loose the finest particles of dust and grit. Although the glass emerges cleaner, larger contaminants remain stubbornly mixed within the flow, requiring a different approach. Here, human hands take over where the machines cannot. Workers stand along the conveyor's edge, their eyes trained to spot and remove stray pieces of paper, plastics, and other foreign materials. This synthesis of mechanical screening and manual effort yields a purer batch, ready for the next stage. But a more subtle impurity still hides among the fragments: countless metal bottle caps. A high-powered magnetic separator provides the solution. Its invisible field plucks the bits of steel from the stream as the glass tumbles onward, leaving the material approximately 80% clean. From here, the glass moves toward a crucial transformation. Larger pieces are fed into a hammer mill, a colossal machine where high-speed rotating hammers smash the glass relentlessly, reducing it to tiny fragments. Any piece that remains too large is automatically detected and cycled back through the mill until it reaches the proper size. This process ensures a uniform flow of fine, sparkling particles known as cullet, which looks almost like man-made sand. By breaking the glass down so small, it can melt much faster in a furnace, saving up to 40% of the energy compared to using raw materials. The cullet is then carried into a powerful suction system, where it is blasted with a strong current of air. This airflow effectively strips away and blows off any lingering fragments of paper labels, polishing the material even further. Finally, the cullet enters the optical sorting system, the most precise step of the entire operation. As the glass pours downward in a shimmering cascade, laser sensors continuously scan each tiny fragment, identifying its exact color and composition. The moment a shard of brown glass, green glass, or even a stray piece of ceramic is detected, the system fires a precise puff of air, shooting the unwanted particle into a separate stream. The speed is astonishing, with tens of thousands of pieces processed every single minute, ensuring the cullet is sorted by color with near-perfect accuracy. Once sorted, the tiny glass particles continue along the conveyor belt. They are directed into separate storage areas, divided by color, where they form massive stockpiles. There they wait, glittering mountains of material ready to be transformed into brand new glass bottles. It is a substance born of sand, yet it cannot be made from sand alone. Before these ground fragments, known as cullet, can enter the furnace, they must be carefully blended with other raw ingredients. The foundation of the mixture is pure silica sand, the element that grants glass its signature clarity. To this, soda ash or sodium carbonate is introduced, a key component that lowers the melting point and conserves energy throughout the entire operation. Limestone joins the blend as well, lending strength and stability to the final formed glass. Depending on the desired formula, manufacturers might also add dolomite, alumina, or metal oxides to fine-tune the color and physical properties. Yet the most vital ingredient remains the recycled cullet, which can constitute anywhere from 20 to 70% of the total batch. Its presence allows the melt to flow more quickly, reducing energy demands by up to 40% compared to using only virgin materials. In fact, increasing the cullet content by just 10% can lower energy consumption by about 3% and make a significant cut in carbon dioxide emissions. Following precise factory specifications, the components are mixed until perfectly uniform, creating a batch ready for the inferno. This blended material is then fed into a massive gas furnace, where the atmosphere rages at approximately 1,750 degrees Celsius, a heat that surpasses molten lava. Technicians oversee the entire process, pouring the mixture into specialized crucibles. Within the facility, workers must be clad in fireproof suits and heavy gloves, as the surrounding heat, nearing 3,000 degrees, is almost unendurable. Once the ingredients stabilize, the mouth of each crucible is sealed to maintain the extreme temperature and control the melt. After 24 hours, the mixture is no longer sand. It now flows with the thick, viscous consistency of lava. The brilliant radiance at the furnace floor is liquid glass, a dense, shining mass that has achieved the ideal temperature and viscosity. For the next 5 hours, the glass remains in this molten state, allowing any residual gases to escape and ensuring the utmost purity of the final material. To give this liquid fire a form, a mold is essential, making its creation the next critical step. Engineers employ advanced CAD software to design the mold with absolute precision, defining every line, dimension, and thickness to meet strict technical standards. From this digital blueprint, the molds are manufactured using cast iron or alloy steel, materials capable of withstanding temperatures up to about 1,400 degrees. These molds are then prepared to receive the molten glass and shape it from within. Once completed, the molds are meticulously installed into the double-blow production line, one of the most reliable and widely used methods for forming hollow glass products like soft drink bottles, food jars, and pharmaceutical containers. The forming process ignites as gobs of molten glass are dropped into an initial blank mold. These gobs are sheared from a continuous stream of liquid glass, glowing at around 1,011 degrees Celsius, and possess the perfect viscosity for smooth and consistent shaping. Inside this preliminary mold, a jet of compressed air is blown from above, pushing the hot glass outward to conform to the mold's walls. This action creates the initial shape, a hollow bubble-like structure known as a parison, which already has a narrow neck. Still glowing with intense heat, the glass is gently transferred to the final mold, positioned just a few inches away on the same production line. Here, a second burst of compressed air is shot directly into the parison center, stretching the softened glass until it presses tightly against every contour of the mold's inner cavity. In a matter of seconds, the bottle's full shape materializes. Though it appears effortless, behind the scenes, every valve and sensor is timed with incredible accuracy, synchronized down to 1,000th of a second. This extreme level of control makes it possible to manufacture hundreds of thousands of bottles per day. Each one so nearly identical and flawless, they seem to have emerged from a single perfect mold. Freshly released from the mold, the glass bottles radiate a deep red heat, their surfaces shimmering in the dark as if they were glowing metal rods. Robotic arms then move with seamless, programmed precision, gliding effortlessly into place. Each bottle is lifted with care and set down onto a conveyor belt. The entire scene unfolds in a calm silence, perfectly synchronized and without a hint of haste. The conveyor belt slowly guides the newly formed bottles, their bases still aglow with heat, toward the cooling area. They travel through a long yellow tunnel where the temperature is lowered incrementally, giving the glass time to settle safely without breaking. This careful cooling stage is unhurried, lasting for several minutes and sometimes extending to tens of minutes before it is complete. As the process continues, the cooled glass bottles arrive at the inspection stage. Here, an array of optical sensors and high-speed cameras examines each one in real time. Every detail is checked, and the moment a defect appears, be it a crack, bubble, scratch, or even a tiny warp, the system immediately flags it and removes the bottle from the line. The next stage focuses on a close examination of the bottle's mouth. Each one is rotated with precision by an automated system, while optical sensors and mechanical probes work in tandem to detect flaws, whether a chipped edge, a fine crack, or the smallest deviation in dimension. Only bottles that pass this strict check are allowed to move forward. After clearing all inspections, the glass bottles are carried to the palletizing section, where robotic systems take charge. Designed for accuracy and uniformity, these machines organize thousands of bottles with ease. A clamp mechanism with suction cups lowers, grips a full row, and sets it carefully onto the pallet layer. To protect against impact during handling and shipping, a sheet is placed between each layer. When the stack is finished, an automated wrapper secures the pallet in film and tags it with a code corresponding to its production batch. Finally, the glass pallets are moved into storage, neatly stacked and ready for shipment. From there, they will travel across the globe, soon to become sparkling bottles, filled to the brim and ready to serve in every corner of daily life. It is a taste recognized across the globe, sealed within a vessel of iconic glass. But before this bottle reaches a single hand, it must survive a gauntlet of mechanical precision. The journey begins with a thorough cleansing, as high-pressure hot water and steam scour each bottle to eliminate any trace of dust or bacteria. They then move down a high-speed conveyor to the filling station, where automated nozzles dispense the famous soda with milliliter accuracy. At the same moment, an injection of carbon dioxide gas locks in the signature fizz. Without pause, the bottles head straight to the capping station. Here, precision machines press crown caps firmly into place, a process immediately followed by a detailed inspection. High-precision sensors integrated into the line scrutinize each cap for tightness, guaranteeing a perfect seal that prevents even the smallest leak. Next, every bottle passes before a high-speed camera system, which checks for cracks, improper filling, or misapplied labels. The bottles glide smoothly onward, a programmed assembly in perfect formation, moving with a steady, precise rhythm. As they reach the water spray station, a high-pressure jet of cold water is aimed directly at the neck of each passing bottle. Finally, the perfectly sealed Coca-Cola bottles are packed into cartons, loaded onto pallets, and moved into cold storage. They now stand ready to be shipped to millions of stores worldwide, from small roadside shops to luxury hotels. What was once shattered and discarded now stands whole again, a testament to a remarkable cycle of renewal. From a chaotic collection of broken shards, a form of pristine and luminous clarity emerges, imbued with new purpose and inherent value. This transformation from waste into a perfect vessel is more than a victory for ecological balance. It is a quiet monument to human ingenuity, a process where industrial power and environmental stewardship find common ground, turning the remnants of our past into the foundations of our future.